So I'm going to start by showing you some of the equipment we use in this lab. So to begin with, down here at the end of the track, we've got the Go motion sensor. And this thing basically works the same way that a bat does, in the sense that it sends out sound waves, so a little clicking noise you can hear. And if there's some object in front of the sensor, then it will reflect those sound waves back towards the sensor. The sensor can detect that and then figure out how far away the object is from the sensor. And it can do this repeatedly in real time. So this is great in that we could, for example, put the sensor at the end of a track, and in conjunction with a computer program that I'm going to show you in a moment, you can map out in real time how far away this cart is. So you could move the cart towards or away from the sensor and actually see a real-time graph on your screen where the position gets larger or smaller depending on how far away the cart is. So if we can get a position time graph for the cart, then we could also get velocity time graphs. We can study its acceleration. So this motion sensor is a really good tool for studying kinematics. Now, we're not going to be using the cart and the track right away. We will use this later in the lab. But to begin with, what you do is you point this at one of your lab partners and you have them walk towards or away from the sensor, and you capture that on the screen. So you'll get a real-time graph of your partner moving around the room. So there's a few things you need to be aware of with the sensor. One is that there's something called the dead zone, which is basically an area close to the sensor where it's not able to detect things accurately. So the lab manual says the dead zone's about 10 centimeters away. I find that about 15 centimeters is a little bit safer as a margin of error. So that just means if you've got an object that's closer than about 15 centimeters to the sensor, it won't accurately detect that. You'll see on the screen it just goes flatlined. So if you want to measure how far away something is, it has to be at least 15 centimeters away, and the sensor is usually good up to a few meters. So you'll be pointing this at a partner, make sure that they're at least 15 centimeters away from the detector when they start, and they might, for example, walk away from the sensor, and you would capture that motion and be able to see on the screen how accurately they're moving at a constant velocity, for example. Another thing to be aware of is that this sensor can be fooled by other objects that are in the vicinity. So when you're pointing it at your partner, make sure that they are walking through a relatively clear area, like one of the aisles between the desks. Because if you're too close to the edge of a desk or a chair, the sensor might get confused by that, pick up those other signals, and then you'll get a really strange looking graph. Another thing to be aware of is that this little window flips up, and there's two settings. So one of them is the cart on the track setting. So over there, when you're studying the cart on the track, you want to use that setting. When you're studying a person, however, you want to make sure you're on this setting. So just make sure that you're on the people setting to begin with the sensor, and then you can flip this down and point it at your partner. The positive direction is defined as being away from the sensor. So this is your origin, and your partner, if they're walking away from the sensor, is walking in the positive direction as far as the computer program is concerned. So now I'm going to show you what motion of the cart on the track looks like on screen, just to give you an idea of how this works all together with the computer program. So all of the computer programs you're going to need this semester are all housed in one folder on your desktop called the 1100 folder. So you look around for a folder that says 1100, open that up, and there's a variety of programs in here and also a whole bunch of folders when we've got more than one thing that we need to look at it for a particular experiment. Now for this first week, we're going to look at the velocity program. We're going to use that. So you can double click on the velocity program and wait for it to open. And you get something that looks like this. So you've got a great big position time graph over here, and we've also got a data table, which is going to show us the actual raw numbers that were used to plot our graph. Up here in the corner is this little collect button. So if I press collect, then the sensor is going to start emitting its little noise, a little clicking noise, and it will detect how far away, in this case, the cart on the track is. So I'm going to show you this. So I'm starting with my cart roughly in the middle of the track. I'll press collect. And here's me moving the cart towards the sensor, and here's me moving the cart away from the sensor. So as it gets farther away from the sensor, the position over here got much larger. When it was getting closer to the sensor, it got much smaller. So in real time, I'm able to see how far away that cart was. So now let me show you that dead zone I told you about. I'm going to move the cart from the end of the track right up close to the sensor. And you'll see at a certain point, the graph just flatlines because it can't detect something that's too close. So I'll press collect up here at the top and move my cart towards the sensor. And at a certain point, I get right up close to the sensor and I can move the cart back and forth a little bit, but it just looked all flat there, right? So, like I said, the lab manual tells you that 10 centimeters is where the end of the dead zone is, but it's actually closer to about 15 centimeters with this apparatus. Now, another thing that you may need to do is you may need to adjust the size of the scale. You can actually hover your mouse over top of the little tick marks on the axis and then click and drag. But personally, I find that a little bit of an annoyance and really slow. There's a faster way to do this, and that is you take your mouse and you go up to the highest number and you click on that number, and it will allow you to change how big the biggest number is. So I can type in 1, hit enter, and now 1 is now the highest point on my graph. So like I said, you can just click and drag things, but I personally find it faster to just click on the highest or the lowest number and change the default value that it's displaying up there. Now, as I said, in this first part of the experiment, you're going to be pointing the sensor at a partner, and they'll be walking away or towards the sensor, as dictated by the lab manual, and you'll be capturing that motion on screen with the computer program, and then sketching what you see into your lab book here. So in this first question, what they have you do is they have your partner walk away from the detector at a constant velocity, and then they have them do it again, except at a slightly faster speed. So you want to draw both of those lines onto this graph, and then you're going to comment on the similarities and differences between those two lines. Now, when you're drawing this, go ahead and draw the little bumps and wiggles you see. So draw what you actually saw on screen. It doesn't have to be idealized in any way. Then they have you talk about similarities and differences, and specifically, it's a good idea to talk about how you can tell which line is the one where the person was walking faster. In question 2, they're saying if you were to walk left, that is in the negative direction towards the detector, what would the graph look like? And they do have you do something that is going to be very common throughout this whole semester, and that is they give you a space to make a prediction. And then later on, you're going to do the experiment and actually draw what you really saw on screen. Your prediction should be the ideal world case, so what you expect to see theoretically. So ideal world means no bumps and wiggles, no friction, no wonky stuff because your partner couldn't exactly walk at a constant velocity. So you draw the perfect world case that you expect to see, and remember that constant velocity should be a straight line on a position time graph. And then you actually do the experiment and draw what you really did see, including bumps and wiggles and any weirdness of the data. And then they ask you to make a comparison between them. So when you make this comparison, you're comparing what you actually saw to what you predicted that you would see. And you want to talk about similarities and differences. So in what way was your real-world graph similar to the theoretical one? And in what ways did it differ? So the differences might be the bumps and wiggles, for example. It's never enough to say my graphs look the same. You have to be specific, and I recommend you use graphing language. So say things like, they were both linear, or they were both curved, or they both had a y-intercept that was positive, or they both had a y-intercept that was 0. One thing that you don't need to talk about is whether or not the slopes were the same, because we don't have any numbers on here. So these are just sketches. We don't know what the slope values are. So if this slope looks way less steep than this one, that's actually not something that's physically relevant just because we don't know what the slopes are. So don't talk about slope, but do talk about things like the y-intercept, whether it's linear, whether the slope is positive or negative or 0, things like that. And then I won't say too much more about everything you do up to question 9, just because it's very straightforward. Now, when you get to question 9, things get a little more sophisticated. So for this one, you're going to be using the cart on the track. And for that reason, you need to grab your sensor, open it up, and make sure you're on the cart setting now, because you had been on the person setting. Then you can put this back at the end of the track. And before you start taking data, though, there's something you need to do every time you use the cart on the track, and that is you need to level your track. And we do it via this guy here. So I'm going to stop the video here and insert another little bit of video that shows you how to level your track correctly, and then I'll come back and show you the rest of the experiment. Anytime you're using the cart on the tracks, you want to make sure that your track is well leveled before you start taking data. So before you begin, Take off that, and you're going to want to level this guy. The way in which you level it is, if you look, you'll notice that there are screws on the bottoms of the legs. So the first thing you do is try and rock the track back and forth horizontally. It shouldn't wobble. If it does, adjust your legs so that it's nice and stable to begin with. Then you want to adjust them higher or lower on one end in order to level the whole track. The way in which we do that is we have this bubble level, and you just lie it flat on the track, and I'll show you a close-up in a moment, and adjust the legs such that the bubble in the middle of the bubble level is centered between its two lines. Now here's the level lying on the track, and we're going to want to level it in two directions, one along the length of the track and one horizontally across its skinny dimension. So I'll zoom in a little bit here, and you can see that the bubble is between the two lines. That means I've done a good job of leveling it. If it wasn't centered between those two lines, you'd want to adjust the legs a little more to get it centered. And if I come down the track a little bit, this bubble also is relatively centered between its two lines. It's less important that this one is centered than it is for the other one. But as much as possible, you get both of them so that the bubble is right between the lines to make sure that your track is perfectly level before you start taking data. Okay, so now we're back, and you've leveled your track. You want to make sure that the vicinity of the track is fairly clear of objects. So for example, if somebody puts their hand here, there's a possibility that the sensor will pick up stray reflections off of their arm and give you a strange looking graph. So make sure that there's nothing in the immediate vicinity of the track, just so that it won't be confused. It will only give us readings off of the cart. And what you'll be doing is you'll start the program running, and this is the sort of motion you want to capture, is a slow exaggerated push and then a release. And it's important that it be a slow exaggerated push so that you can capture that motion. So you start with your cart about 15 centimeters away. You'd start your program running by clicking the collect button, and then it would be a slow exaggerated push and a release. And if you think about it, when your finger is actually on the cart accelerating it, you should see acceleration on your graph. Now, constant velocity on a position time graph looks like a straight line, but acceleration on a position time graph is always going to look like a curved line. So when your finger's actually on this, we expect to see some sort of curvature on the graph, and when we let go so that it's just rolling on its own, hopefully without friction, we should see a straight line. That's what we theoretically expect to see. So in your book, before you actually take data, you will make a prediction on what you expect your graph to look like. Then you capture it on screen, and then you're going to actually compare these two. Now, one thing that is unfortunate is you're not allowed to actually print out the graph this week. In future weeks, we will allow you to just print your graph, paste it into your book. This week and this week only, you're going to actually hand graph what you see on the screen into your book. So we'll give you graph paper, you'll use the data table on your screen, and you'll actually graph this by hand. So now I'm going to show you how to print your data table for question 9. But first I'll just mention that this is not the graph that you will see in question 9. This is just a graph I happen to have up here. So this is nonsense. It's got nothing to do with question 9. But I'll use this to explain to you how you actually print out your data table. So one thing to notice is if I click and drag my mouse, I can highlight certain sections of data. And when I do that, that same data gets highlighted in the data table. So I'll highlight a little bit here, and you can see that that same section of data got highlighted over here. So in your graph for question 9, you're going to have a little bit that's curved due to acceleration and a little bit that's straight due to constant velocity. And you want to highlight a little section of your data that has some straight in it and maybe just a little bit of curvature at one end. You're going to be graphing things by hand, and that means you want to graph the data that you've got in this data table. Now, if you are doing this lab the paperless way, that is, that you're just pasting screenshots of your work into an electronic lab manual, then all you need to do at this point is just screenshot your data table. So Shift Windows key S on the lab computers, and then you highlight just this area of the data, and then you can paste that into your lab workbook. And then, like I said, you're going to make a graph of the first 10 to 12 data points here. Once you've finished your graph, you're also going to, by hand, draw a slope line to the linear part of your data, not the curved bit, but the straight part. And you do a slope calculation and find the velocity of your cart at that point. And then the very last question in the manual tells you to draw some conclusions. Basically, you're going to be comparing the graph that you predicted would happen to the graph you actually saw and seeing what's the same and what's different. Some students find the wording a little confusing when it says draw conclusions. That doesn't mean draw a picture. It means state conclusions. So you're basically answering all the questions in that last question of the lab manual using words, not pictures.